Section 3.3 is solving inequalities using multiplication or division. I can use multiplication or division to solve inequalities. Those are our learning targets and what we're hoping to be able to do today. Big ideas here. In the same way multiplication and division are used to solve equations, multiplication and division can be used to solve inequalities. The only difference here is when multiplying or dividing by a negative number, it's necessary to reverse the inequality sign. So, the take note on page 178 talks about our multiplication property of inequality. We can multiply both sides of an inequality by a positive number and get equivalent inequalities. So if we multiply both sides by a positive number, our inequality stays the same and we have an equivalent inequality. If we multiply both sides of an inequality by a negative number, we've got to flip the inequality symbol in order to get equivalent inequalities. Think about this if I had something like 2 less than 6. Okay, now if I multiply both sides by negative 1, I get negative 2 and negative 6. In order to keep this equivalent, keep it true, negative 2 is actually greater than negative 6. Okay, so we have to be careful there and flip that inequality. If we multiply, and it's going to work the same way with division, both sides by a negative number. So if we multiply or divide by a negative number, we flip the inequality. I have this up on the wall in my room, the very first poster, because it's that important. The take note on page 180 talks about our division property of inequality. Here it's the same rules as multiplication. So again, we can divide both sides of an inequality by a positive number and get equivalent inequalities. But if we divide both sides of an inequality by a negative number, we still have to flip the inequality symbol in order to get equivalent inequalities. So if we're multiplying or dividing by a positive number, we keep our inequality. If we're multiplying or dividing by a negative number, we flip it. In example 1 here, we check what is happening to my x right now. It's being divided by 3. We get rid of division by multiplying. Whatever I do to one side, I still do to both. So 3 divided by 3 is 1 times x gives me just x. Since I multiplied by a positive 3, I keep my inequality. And I get negative 6. Okay, so our number here didn't change signs. It was negative, it stayed negative. So we keep our inequality symbol there. I know the 2 is negative, but the number that we multiplied by was the 3. So here are our solutions. Now we also need the graph. So this is our solutions. To graph, I put negative 6, my boundary point, the next number on each side, and 0. I'm going to put a circle at my boundary point. Because I don't have an equal to there, I'm not going to fill it in. I want numbers less than negative 6, which are numbers like negative 7 or negative 100. So we shade everything to the left. Now in example 2, what's happening to my variable? Well, it's being multiplied by a negative 3 over 4. We get rid of multiplication by a fraction by multiplying by the reciprocal. So I'm going to multiply by negative 4 over 3 on both sides. Negative 4 over 3. Take the sign with that number. So if we have a negative number, we multiply by a negative to make it positive. 4's cancel and my negatives and my 3's cancel. All I have is 1w. Here, we switch our whole number into a fraction by writing it over 1. Multiply straight across. Negative 12 over 3, which is negative 4. And we can cancel there too if you'd like. Now, because I multiplied by a negative number here, I've got to flip my inequality. So instead of being greater, now I have less than. And we always keep the equals part if it's there, or not if it's not, but we flip the inequality. And again, that's because we multiplied by the negative here. So anytime our coefficient, the number that's being multiplied by our variable, is negative, we're going to end up flipping our inequality. So we can look at a problem and know right away, are we going to flip or are we not? As soon as we have all of our variables together, if our coefficient is negative, we flip. If it's not, we keep. So here's my solution. Now we need to graph solutions and my graph. Again, my boundary point goes in the middle. -3, -5, one number on each side, and 0. I'm going to put a circle at -4, and because I'm equal to here, I'm also going to fill that in. We want numbers that are smaller than -4, numbers like -5 and -100. So we go to the left and shade everything there. And again, if we want to check that, we have to plug in both our boundary point and a test point. The boundary point should be equal when we plug it back in, and one of the points on our solution, if we pick -5 or -100, should make a true statement. Now, feel free to pause here and give this a try if you'd like. C is being divided by 8, and we get rid of division by multiplying. Whatever I do to one side, I have got to do to both. And again, we can write that whole number as over 1. So C, since I multiplied by a positive 8, my coefficient here, the number with my variable was positive. I keep my inequality. Multiply straight across, 8 over 4 gives me just 2. So here I get C greater than 2. If we plug it in, I get 1/4 equals 1/4. So I know my boundary point is right. Now, put our boundary point on there, the next number on each side, and 0. We keep it open because I don't have a little equal to there. Now, as far as shading goes, we want our answer or our shading or our solutions to be greater than 2. Numbers like 3 and 100 are greater than 2. So we shade everything to the right here. Now if we check, if I do like 8 over 8 gives me 1, which is more than 1/4. So we know that we're right if we check a value there. Again, feel free to pause and give this a try if you'd like. Right now, n is being divided by 6. And we have a negative there, so I'm going to say it's being divided by a -6. In order to get rid of division, we multiply both sides. So I'm going to multiply by a -6 and multiply by -6. Again, I'm going to take the sign with that number, so all I have is an n on my left side. -6 divided by -6 cancel, and all I have is an n. -1 times -6 gives me a +6. So here, if I look, I started with a negative number and I switched it to be positive. Okay, my sign flipped. So I have to flip my inequality because we multiplied by that negative. Instead of being less than, now I have greater than. Anytime we multiply or divide an inequality, we flip our inequality. If it's negative, if we multiply or divide by a negative, we flip our inequality. Okay. Put our boundary point, one number on each side, and 0. Circle at 6. I'm going to keep it open here because I don't have an equal to line. We want numbers, or our shading, or our solutions, they all mean the same here, to be greater than 6. Numbers like 7 or 100. So we shade everything to the right. And if we check 6, if we plug it in, gives us -1 equals -1. Perfect for our boundary point. And if we pick a big number like 12, for example, I get -2 is less than -1, which is also true. So we are correct. In example 3, it says, you walk dogs in your neighborhood after school. You earn $4.50 per dog. how many dogs do you need to walk to earn at least $75? So here we want to earn at least $75. Could we earn exactly $75? Yeah, that's the smallest amount we could earn. Could we earn $80 or could we earn $60 to make that true? Well, if we want at least 75, we could earn 80, but we can't earn 60. 60 doesn't get us there. So it's got to be greater than or equal to. At least means greater than or equal to. 75 is the smallest it can be. Again, if you're not sure, plug in some test values like that and see which one makes it true. Now, we earn $4.50 per dog. So $4.50 times the number of dogs. Don't forget to define your variable. Now, my variable here is being multiplied, so I get rid of it by division. And since I'm dividing both sides by a positive number, I can keep my inequality here. And when I divide 75 by 4.5, I get 16.6 repeating. Can I have 0.6 repeating dogs? I can't. So here we look. Because I need it to be greater than that 16, I actually need it to be at least 17 dogs. Because we can't just walk 0.6 dogs. So D is at least 17 dogs, or we could say D is greater than or equal to 17 dogs. How many dogs we need to walk? At least 17. Here we want the solutions and the graph. My variables being multiplied, I get rid of multiplication by dividing. And whatever I do to one side, I do to both. Keep in mind we take that sign with the number. It's a negative 9 times y. Negative 9 divided by negative 9 gives me just one y, which is perfect. I just have a y on that side. 63 divided by negative 9 is negative 7. And since I started positive and I'm divided by a negative, I have to flip my inequality, greater than or equal to negative 7. When we multiply or divide by a negative number, we flip our inequality. If we plug in negative 7, I get 63 equals 63. So I know my boundary point is correct. That's my solutions. Now, the graph, I'm going to put my boundary point, the consecutive number on each side, and 0. Keep in mind when we have negative numbers, 0 is to the right. I put a circle at negative 7 because that's my boundary point. Here, I have an equal to line, so I fill in my circle because that's part of my solution. Remember, everything that's filled in is a possible solution. And we want our numbers to be greater than negative 7. Numbers like negative 6, 0, and 100. So we shade everything to the right. If we plug in a number and check, like 0, I get 0 is less than or equal to 63, which is true. So we have a true statement there, and we know that we're right. I'm going to stop here, and I'll finish with another video.